So we are group 2, and the first topic that we're gonna discuss is bond theory of electrical conductivity and periodic trends of metals. And also the periodic trends of some metals and their reactivities. What is bond theory? Bond theory explains how and why materials conduct electricity based on the arrangement of electrons in energy levels. In atoms, electrons occupy specific energy levels, but in solids, especially metals, atoms are packed closely, so their energy levels overlap and form bands. Conduction band, the next higher band where electrons can move freely. The band gap. The band gap is the energy difference between the valence band and the conduction band. Whether a material conducts electricity depends on the size of the band gap. Types of materials. First, conductors. The valence band and conduction band overlap. Electrons move freely, good conductors. Second is semiconductors. Small band gap. Electrons need a little energy to jump to the conduction band. Conductivity increases with temperature. And third is insulators. Large band gap. Electrons cannot jump easily to poor conductions. Well, I'm just gonna discuss po the summary of band theory. No band gap means good conductor. Small band gap means semiconductor. And also large band gap means insulator. The part 2 po is periodic trends of metals and their reactivities. So what is periodic trends? Periodic trends are predictable patterns in the periodic table that show how elements behave. Important trends of metals. First is metallic character increases down a group. Then this decreases naman across a period, left to right. The reason, metals lose electrons easily. Second naman po is reactivity of metals. The transition metals to less reactive but important for industry. So how reactivity changes? Then across a period, reactivity decreases naman. Metals on the left react more than those on the right. So why do metals react easily? Because metals want to lose electrons to become stable. And also metals with lower ionization energy reacts more quickly. Samples of metal reactivity. Sodium reacting with water. 2 extremely reactive. Another example of metal reactivity, magnesium reacting with acid to moderate reactivity. Another example of metal reactivity, gold to very low reactivity, does not corrode easily. Conclusion. Band theory explains electrical conductivity using the concept of valence band. That's all po sa topic 1.
Good day everyone. Today, we delve into a material that is literally the foundation of our modern world, alloys of steel. We refer to steel as the backbone of modern industry. Steel is fundamentally an alloy of iron and carbon, but alloy steel takes this a step further. These additive elements are what make steel so adaptable. Let's look at 3 essential ones. First, chromium. It dramatically increases corrosion resistance and is defining component in creating stainless steel. Nickel is added to enhance the material toughness and impact strength, a property vital for resisting shadow shock, especially in cold environments. While molybdenum is highly valued for its ability to provide exceptional heat resistant and improve the steel strength retention even at extremely elevated temperature. We categorize steel based on its composition and application. Carbon steel is the most common classified by its carbon percentage and form the basis for construction and basic parts. Alloy steel is the broader category we are focusing on. Further split into low alloy, less than 5% additives. For general high strength and alloy more than 5% for specialist uses. Stainless steel is high alloy type defined by containing over 10.5% chromium, giving it its famed corrosion resistant. Finally, tool steel is engineered to be exceptional hard and resistant to abrasion for use in manufacturing implements like cutters and molds. On stainless steel, its unique rust-free property is not inherent but is a result of a self-healing mechanism. When exposed to oxygen, the chromium in the alloy rapidly forms a thin, tough, passive layer of chromium oxide on the surface. This layer prevents corrosion and, if scratched, immediately reforms. The image clearly shows stainless steel in a critical application, such as surgical instruments, where hygiene and corrosion resistance are paramount. Tools steel represent the pinnacle of hardness and abrasion resistance. It is especially designed to cut, press, and shape other materials. Often under intense heat and friction, its primary characteristic known as red hardness, which means it retains its hardness and structural integrity even when heated to temperature where the metals grow red. Structural steel is responsible for, literally, building the world. This steel is optimized for load-bearing capabilities. It requires a critical balance. It must have high strength to support weight, but also sufficient ductility, the ability to bend slightly, to prevent brittle fracture under stress, especially during seismic events or extreme weather. And perform requires are extreme, as in the aerospace industry. We turn to alloys like merging steel, which is standards for martensitic agent. This alloy achieves ultra-high strength, often extending 2,400 MPa in tensile strength, combined with exceptional toughness. Ang margining steel is isang ultra-strong na bakal na may hanggang 24 MP. Pagtaas ng MP, pagtibay. Ito ay ginagamit sa mga rocket at sensitive na kagamitan. Dahil sobrang lakas nito at hindi basta-basta nababasag. This slide clearly illustrates the performance gain achievement through alloying. The unit we use is megapascal or MPa, which measure the material strength or ability to resist stress. Only from raw or toughness steel beams is complex. The process involves three primary stages. First, iron making, where raw iron ore is melted in a blast furnace. Second, steel making, where oxygen is injected either via basic oxygen, steel making, or an electric arc furnace to remove impurities and precisely control the alloy content. Finally, rolling, where the hot, finished steel is passed through heavy rollers to shape it into usable sheet, bars, or structural beams we see in construction site. Steel innovation has been continuous. Key milestones include 1865, when the Bessemer process enabled the first mass production of steel. To summarize it, steel is defined by three key attributes. First, it is immensely versatile, used in everything from everyday kitchenware to high-stress aerospace components. Second, it is highly customizable. The precise combination of alloying elements allow engineers to tailor a specific property for almost any job. And finally, steel is incredibly sustainable, as it is 100% recyclable without loss of quality, confirming its status as an eco-friendly material choice for the future. And that's conclude our overview of alloy.
Hello everyone. Today I will be discussing one of the key topics assigned to Group 2, the properties of metals. Metals play a major role in our daily lives, from the wires in our gadgets to the structures of building and even in transportation and tools. Their usefulness comes from the special physical and chemical properties they possess. First, physical properties of metals. First, let's talk about their physical properties. Lustre. Metals are shiny when polished. This is why gold and silver are used in jewelry and why aluminum is used for decorative surfaces. Malleability. Metals can be hammered into thin sheets without breaking. For example, aluminum foil and gold leaf are both result of this property. Third, ductility. Metals can be stretched into wires, copper, wires used in electrical wiring are a perfect example of good conductors of heat and electricity. Metals allow heat and electricity to pass through them easily. This is why cooking pots are usually made of stainless steels and electrical cables use copper or aluminum. High density and strength. Most metals are heavy and strong. This makes them ideal for construction materials such as steel beams in building and bridges. High melting and boiling points. Metal generally requires very high temperature to melt. Iron and tungsten, for example, can withstand extreme heat. Second, chemical properties of metal. Now, let's move on to the chemical properties of metal. First, reactivity with oxygen. Metals react with oxygen to form metal oxides. For example, iron reacts with oxygen and moisture from rust. Second, reaction with water. Some metals like sodium react very quickly with water, while others like zinc and iron react slowly. Meanwhile, metals such as gold and platinum do not react with water at all. Third, reaction with acids. Most metals react with acid to produce a salt and hydrogen gas. For instance, zinc reacting with hydrochloric acid releases hydrogen bubbles. Tendency to form positive ions. Metal easily lose positive ion, which is why they are often involved in electrical and chemical process. Third, why these properties matter. These properties determine how metal are used in real-life application. Their strength and durability make them essential in construction. Second, their conductivity makes them crucial in electrical system. Third, their malleability and ductility allow them to be shaped into tools, wires, and household items. Here are the added examples for the physical properties. For lustre, additional example, stainless steel utensils, mirror, and metal coins shine because of metallic lustre. Malleability, copper sheets used in roofing and decorative metal art are made by hammering copper into thin layers. Ductility, aluminum wires used in power transmission lines are stretched into long cables due to high ductility. Conductors of heat and electricity. Silver is actually the best conductor of electricity, which is why it's used in high-precision electronics. Iron skillets heat even because metal conduct heat well. High density and strength. Titanium is strong yet lightweight, making it ideal for aircraft parts. Steel is used for ship hulls, railway tracks, and heavy machinery. High melting and boiling points. Tungsten filament in old light bulbs were used because tungsten has the highest melting point of all metals. Nickel and chromium alloys withstand high furnace temperatures. Chemical properties. Reactivity with oxygen. Aluminum forms a thin oxide layer that protects it from further corrosion, which is why aluminum does not rust easily. Reactions with water. Here's the additional example for this. Potassium reacts even more violently than sodium, producing flame. Second, magnesium reacts slowly with hot water but not with cold water. Reaction with acids. Iron reacts with dilute sulfuric acid to form iron sulfate and hydrogen gas. Formation of positive ions. Sodium, calcium, and aluminum easily form positive ion, which is why they are used in battery and electrochemical cells.